Above us drifts the oldest light in existence, a silent glow from a universe that existed long before Earth had oceans or names. Every faint flicker carries a story of galaxies that shouldn't be there, stars born too early, and worlds whose skies burn with elements not found on our periodic table. What happens when we build a telescope powerful enough to unravel these cosmic secrets? James Webb has given us more than answers. It has given us questions we never knew to ask. Like and subscribe if you've ever wondered, what if the universe is stranger than we dared imagine? Let's begin. In the silence of space, 13 billion years of light drift toward us. Somewhere in that cosmic ocean, the James Webb Space Telescope caught a whisper from the beginning. Galaxies so ancient their light arrived before Earth had formed a name for itself. We stare into them now, as though we're staring back in time, glimpsing the edges of our own cosmic origin. These distant galaxies, small, primitive, and impossibly bright, formed at a time when the universe was only a few 100 million years old, when life on Earth was not even a possibility, when the matter that makes us had not yet coalesced. These galaxies had already ignited their first stars. That light has been traveling toward us ever since, carrying with it the story of how everything began. The James Webb Space Telescope captures that story, not in visible light like Hubble, but in infrared. Infrared is the glow of heat, the radiation left behind when time stretches space so far that visible light becomes too faint, too red to see. Webb is designed to see that ancient warmth, to look past the cosmic fog that blocks our view and reveal what the universe looked like when it was still forming itself. And what it found. These first galaxies were supposed to be small, dim, and undeveloped cosmic infants learning how to exist. But many of them are already mature, massive, forming stars faster than they should. Their light tells us they broke the rules before we even knew the rules existed. How did they form so quickly? Where did they get the energy to shine so brightly, so soon? It's as if the universe went from zero to everything in a cosmic instant. Scientists thought the early universe was simple. Mostly hydrogen, some helium, a few stray particles floating in an expanding void. But the galaxies Webb sees are anything but simple. They contain elements like carbon, oxygen, and even iron, elements that can only be created in the hearts of stars. That means entire generations of stars must have lived and died before the universe was 1 billion years old. Webb isn't just showing us old light. It's showing us a universe that grew up faster than we ever imagined. It's as if the cosmos took a shortcut, skipped a page in the story, and left us the ending without the explanation. These primordial galaxies are like postcards from a time when physics was still deciding what it wanted to be. And every time Webb focuses its golden mirrors on the deep sky, it returns more messages, more riddles, more questions written in the language of stars. We thought we knew how the story of the universe began. But maybe, just maybe, what happened in the beginning is stranger than we ever dared dream. Unlike the bright eyes of Hubble, James Webb sees in the glow of heat, in the hidden warmth of galaxies and dying stars, in the birth cry of planets lost in stellar nurseries. Every object in the universe that's warmer than absolute zero gives off infrared light, a gentle glow that human eyes will never see. But to James Webb, this faint warmth is a map of everything that's ever lived, died, or drifted through the cosmos. Its giant honeycomb mirror, coated in gold for its ability to reflect infrared, is not just a telescope, it's a time machine, tuned to the hidden wavelengths that reveal the universe's most private history. Infrared light is the universe's second language, spoken in whispers, hidden behind veils of dust and darkness. Hubble, for all its majesty, sees only the starlight that reaches us unobstructed. Webb, on the other hand, sees what has been concealed. It sees through shrouds of gas, into the hearts of galaxies that otherwise appear as black shadows. It sees planets basking in the heat of newborn stars, and it sees the embers of light so stretched by time and space that only an instrument this precise, this patient, can catch them before they disappear forever. To do this, Webb must stay colder than anything we've ever put in space, chilling its instruments to just 40 degrees above absolute zero. Its massive sunshield blocks out the Earth, Moon, and Sun, keeping its gaze fixed only on the deep sky. Even a spark of warmth from sunlight or solar radiation could blind it like a flashlight in a dark room. So it lives in a delicate balance, cradled at a gravitational point 1,000,000 miles from Earth, where it can watch, unblinking, into eternity. And what it watches is a universe alive with secrets. In the warm darkness of space, Webb sees stars that never should have been born, planets cloaked in stormy atmospheres, and galaxies so distant they appear as smudges of ancient heat. Webb reveals the skeletal structure of the cosmos, the filaments and threads of gas where everything else is born. It strips away the bright, beautiful distractions of starlight and shows us the machinery underneath. It's as if Hubble sang the universe's song, while Webb pulls back the curtain and shows us the instrument. We look into its data, thick with wavelengths beyond sight, and it feels like eavesdropping on a secret conversation between space and time, between existence and memory. Because in the end, every faint glow Webb sees began its journey long before we existed. See not with eyes, but with understanding. What Webb saw defied expectation. Galaxies so massive, so luminous, so early in time that our physics shouldn't allow them to exist. These ancient cities of stars existed just a few 100 million years after the Big Bang, at a moment when the universe was still an unruly fire of raw hydrogen and energy. They shouldn't have had enough time to grow, to collect the matter needed to shine like cosmic lanterns in a sea of chaos. Fully formed, impossibly bright, already alive in a reality that was barely old enough to cool down. The first galaxies are not small, timid flickers of light like our models predicted. They are giants, with masses equal to modern galaxies like the Milky Way, but appearing more than 13 billion years in the past. That means they gathered their stars and gas, ignited fusion, and sculpted the earliest structures of the universe, all while the laws of cooling, gravity, and matter were still whispering into existence. And so the question becomes, how? How could so much order come from such a brief chaos? How did matter condense so quickly into stars? Where did these galaxies get the fuel to burn so brightly? In a cosmos supposedly too young to even have metals heavier than helium, the James Webb Space Telescope gave us our first close-up glimpse, revealing that the first galaxies may not have played by the same rules. They formed differently. They lived faster, they burned harder, and they used raw materials that no longer exist in abundance today. Back then, the stars were enormous, perhaps hundreds of times the mass of our Sun. They burned with terrifying intensity and died in supernova explosions that seeded the cosmos with the first heavy elements. Carbon, oxygen, iron, the same building blocks now inside your body. These weren't just galaxies, they were cosmic forges, star factories, engines of chemical creation, and yet even that might not explain their impossible speed. Some scientists now whisper about exotic physics, about dark matter behaving differently in the early universe, or gravity being stronger when time itself was still forming. Others wonder if we've misunderstood the timeline, if perhaps the universe is older than we think, or space expanded differently than our equations believed. Webb's findings don't answer the questions. They multiply them. Because now we know the early universe was not empty and slow-growing. It was busy, bursting, reckless, and maybe the laws of physics were written after the first galaxies were born, not before. Perhaps the universe didn't learn the rules until after it started breaking them. Stars formed faster than stars should have, fusing hydrogen when hydrogen itself was barely born. In the earliest moments of cosmic time, the universe was a blazing sea of particles, too hot and too wild for stars to exist. It was chaos, raw energy buzzing and scattering through space. Hydrogen, the simplest and most abundant element, didn't even have time to breathe before it was being swept into the gravitational pockets where the first stars would be born. Yet somehow, impossibly, within a few 100 million years, the night sky was ablaze. Stars, enormous and shocking in their brilliance, bloomed like cosmic flares across the dark background of a still-forming universe. These weren't gentle yellow suns like ours. They were monsters, each one up to 300 times the mass of the sun, burning millions of times brighter. How could they exist so soon? How could they gather so much matter so rapidly in a universe that had barely cooled from its fiery birth? The answer, if we can call it one, lies in what astronomers now call population 3 stars, the very first stars to ever exist, made from nothing but hydrogen and helium, elements forged in the Big Bang itself. They were pure, untouched by the heavy metals that later stars contain. And because of this, they formed with an efficiency and ferocity that no star today can match. These stars didn't just shine, they exploded. Their lives were brief, sometimes just a few million years, before they detonated in supernovas so violent they tore open the night, hurling the first heavy elements into space. And in that destruction, they created the seeds for everything that would come after. Planets, moons, oceans, forests. The James Webb Space Telescope is the first instrument ever capable of detecting the spectral fingerprints of these ancient stars, or what remains of them. It peers into the faint oxygen lines, the dim trace of iron floating in ancient gas clouds, the subtle glow of primordial nebulae. But what Webb found challenges even that wild story. Because the stars it's seeing weren't just forming quickly. Some of the stars Webb sees existed when the universe was just 200 million years old, far earlier than models predict stars could have formed. That means the raw material of the universe must have collapsed into stars almost instantly, as though the cosmos couldn't wait to begin lighting itself up. It's as if gravity took a shortcut. It's as if nature, impatient and bold, leapt into its next phase before the laws of physics had a chance to settle down. Perhaps the early universe was a different place, not just younger, but stranger. A realm where stars were born out of pure energy, where time wasn't yet marching forward as steadily as it does now, where even hydrogen itself couldn't stay still long enough to cool before it was ignited into fusion fire. And maybe, just maybe, the first stars didn't wait for the universe to be ready. They made the universe ready. At the center of the earliest galaxies, Webb found something unbelievable. Black holes the size of millions of suns, spinning before even planets had names. These colossal beasts, called supermassive black holes, were never supposed to exist this early in the universe. According to everything we thought we knew, black holes need time. They're born when massive stars die, and they grow by feeding on gas, dust, or sometimes even entire stars. Under normal conditions, this takes billions of years. But the black holes Webb found? They were already fully grown, when the universe was still a cosmic newborn. Some of these ancient black holes formed less than 500 million years after the Big Bang. At that time, there shouldn't have been enough matter around to create them, let alone to make them so big. Yet there they were, quietly spinning at the hearts of young galaxies, stirring up gravitational storms in whirlpools of light and shadow. How did they get so big, so fast? One theory suggests that the first stars, those colossal, short-lived population 3 stars, collapsed directly into black holes without ever exploding as supernovas. If they were large enough, perhaps hundreds of times the mass of our Sun, they could have skipped the violent death and instead sunk directly into regions of intense gravity, creating the seeds of supermassive black holes. But even that doesn't explain the speed of their growth. These early black holes didn't just sit and grow slowly. They feasted. They devoured gas, swallowed stars, pulled in everything that dared venture too close. And as they consumed, they spun, twisting space-time around them like invisible whirlpools. Some of them spun so fast that their event horizons churned near the speed of light, a phenomenon we can barely detect even in the most advanced simulations today. Their spin isn't just a leftover from their violent birth, it's a record of everything they've ever devoured. And yet, these black holes remain mysterious. Because black holes aren't simply massive, they are the absence of everything, a region of space where gravity becomes so extreme that not even light can escape. They're the cosmic end of the road, where the laws of physics fracture and break. But what if they're more than that? What if the early universe needed black holes to shape itself? Some scientists now propose that supermassive black holes might be engines of creation, not just destroyers. Their gravity may have helped pull galaxies together. Their radiation may have sparked the birth of stars. These ancient black holes might not just be relics of the past, they could be the architects of space itself. Perhaps that's why they arrived so early. Perhaps the universe didn't just form and then make black holes. Perhaps it needed them. Webb isn't just showing us these ancient voids. It's showing us that in the beginning, even before planets spun, before stars sang, there were black holes. Silent, hungry, necessary. Infrared vision reveals what human eyes cannot. The dusty halos of young galaxies, the glowing arches of bent starlight across space. To us, the universe appears as a tapestry of black and white, star-speckled sky with random patches of brightness. But to James Webb, the universe is washed in colors we've never known. Colors made of heat instead of light. These wavelengths are invisible to the human eye, longer than red light and older than memory itself. Infrared is the color of time. When light travels through the expanding universe, it stretches, its wavelength pulled like a violin string until it slips out of the visible range. What began as brilliant blue becomes dim red, then silent infrared. To us, it is gone. But to Webb, it becomes clearer, easier to hear. The telescope's cold, golden mirrors are tuned to catch this stretched-out light, signals that began as brilliant cosmic songs, now humming like echoes across space-time. That's how Webb sees the dusty halos surrounding young galaxies, clouds of stardust so thick they block visible light entirely. Hubble saw darkness there. Webb sees cradles of creation. Inside those dusty cradles, stars are forming, not with gentle flicker, but with roaring, nuclear fire. The dust isn't just clutter, it's womb. It's the raw material for planets, moons, maybe even the building blocks of future oceans and people. Infrared reveals motion frozen in time. When light from a distant star passes near something massive, a galaxy, for example, it bends, just slightly. That warping can turn a point of light into a glowing arc, a smeared reflection created by gravity itself. These Einstein rings or warped shapes are signatures of the unseen structure of the universe. Dark matter, invisible to all but gravity, reveals itself in the way it bends starlight like glass. To human eyes, these bent rays are too faint, too distant, too red. But Webb sees them. Webb sees light that left its source before Earth had continents. It sees the soft glow from galaxies long swallowed by time. It sees nebulae where elements fuse, where chemical bonds spark, where atoms begin to dream of complexity. We thought the universe looked a certain way. We thought it was simple, that we only needed better lenses, bigger mirrors, higher resolution. But Webb reveals that the universe was always layered, some truths visible, others hidden beneath veils of distance and time. Webb isn't just a telescope, it's a translator. It turns the universe's afterimages into messages. It reshapes our ideas of beginning and end. It shows us that what we see is not what is, and that sometimes the truth glows in a color we've yet to name. In these unseen colors of time, we find not only answers, but an invitation to look deeper, to listen softer, to ask what else the cosmos is trying to say. Just beyond the edge of sight, through gravitational lenses, Webb sees ghost-like galaxies, their light stretched and smeared by cosmic warps in space-time itself. These phantom galaxies are not illusions or tricks of the telescope. They're real, just impossibly distant, so far away that their light has traveled through not just space, but space warped by gravity. The universe is not a flat, empty void. It's more like a vast ocean of invisible currents and ripples, created by the mass of everything within it. Galaxies, stars, even black holes bend space like weights on a stretched blanket, and when light passes through that bend, its path curves, revealing to us what lies far, far beyond. This phenomenon is called gravitational lensing, and it's one of the most astonishing consequences of Einstein's theory of general relativity. Light from a galaxy hidden behind another one gets distorted by the mass in front of it, like looking at the world through a droplet of water. The James Webb Space Telescope was designed to exploit this distortion. It gazes through these natural cosmic magnifying glasses and sees what no telescope before it could. Imagine a galaxy so old its stars burned before the Milky Way was even dust. Its light, like a last whisper, is stretched and pulled across billions of light years. By the time it arrives at us, it's almost gone, faint, red, nearly erased by time. But if that light passes through a warp, the deep well of gravity created by another galaxy or cluster of galaxies, the warp magnifies and reshapes it. The ghost-like arcs and streaks Webb sees around those massive clusters aren't errors, they're echoes, they're time capsules. Every curved glow is a message from the past. Some of these ghost galaxies are older than we ever thought possible. They contain stars that lived and died before Earth existed. Their shapes appear smeared, stretched into arcs, their true forms distorted by the curvature of space-time. Yet, even in their distortion, they tell a story. A story of a universe far more crowded than we dared to imagine. A story in which galaxies didn't form alone, but in clusters, in groups, cradled and torn by gravity's invisible threads. With every new arc Webb uncovers, we see not just galaxies, but the hidden structure of the cosmos itself. It's like lifting a veil and discovering not darkness, but more light. A paradox of cosmic nature, that sometimes the most distant things become visible only when the universe bends them for us. And so Webb looks, not at the galaxies in front of us, but at the ghosts behind them. Ghosts whose light traveled through warped space. Ghosts whose stories outlived their stars. Ghosts that remind us, what lies behind what we can see is often the most extraordinary of all. Rather than a calm beginning, Webb shows us a storm of energy, collisions, and starfire. Creation was chaos sculpting shape. For decades, we told ourselves a story that after the Big Bang, the universe slowly cooled, quietly organizing itself into stars, galaxies, and cosmic dust. A peaceful unfolding of space and time. But what the James Webb Space Telescope is showing us now is a very different tale. One filled with violence, heat, turbulence, and change. In those first few 100 million years, the universe wasn't calm, it was wild. Matter wasn't drifting gently into place, it was slamming together, pulled by rivers of gravity into storms of gas and fire. Vast clouds of hydrogen didn't settle. They collapsed under their own weight, igniting nuclear furnaces unlike anything we could call stable. Stars didn't form singly, like seeds sprouting in the dark. They formed in clusters, entire nests of them erupting, flaring, and dying in cosmic seconds. Webb reveals colliding galaxies in the early universe. Young, misshapen objects already smashing together, ripping tidal tales of starlight into intergalactic space. We thought these cosmic dances happened later in life, after the universe had time to spread out and breathe. But no. Galaxies were merging, clashing, and tearing their insides open while time itself was still stretching into shape. Imagine a universe only 400 million years old, less than 1% of its current age. In that universe, stars were exploding faster than new stars could form. Gas clouds were so thick, they glowed brilliant red in infrared light. Radiation tore apart atoms before they could combine. The very fabric of space was uneven, still vibrating from inflation, the rapid expansion that happened in a heartbeat after the Big Bang. It was not a place of quiet wonder. It was a furnace, a crucible, a cauldron where matter was being forced violently into order. And yet, in that turbulence, patterns began to emerge. The first filaments of the cosmic web, the scaffolding of dark matter that now underlies the entire universe, took shape. Gravity pulled gas into invisible threads. Those threads led to nodes. Those nodes ignited in starfire, and from that starfire, dust, not the kind you brush off a shelf, but the kind from which life would one day be built, began to swirl. The beauty of the early universe was not its stillness, it was its storm. And now, whenever we stare into a Webb-deep field image, filled with tiny red dots, unseen arcs, and shimmering galaxies, we're not looking at something peaceful. We're looking at the echo of chaos, frozen in light. The universe wasn't quiet at birth. It screamed itself into being. And in that roar, it wrote the code for stars, planets, oceans, and us. Some stars Webb has found contain no carbon, no iron. They are made of only hydrogen and helium, the universe's first breath. These stars, the so-called population 3 stars, are unlike anything in the modern universe. They existed before the periodic table was written in the cores of exploding giants. They were the first lights to pierce the endless dark, the original fires lit from the unformed void. Pure in their composition, enormous in their force, these stars weren't just made, they were ignited. To understand them, imagine stripping away everything familiar. No gold, no silicon, no oxygen, no iron in the blood, no carbon in the cell. Only the two simplest elements, forged in the first seconds after the Big Bang, hydrogen and helium. And from these, somehow, stars emerged. Not gentle suns like ours, but monsters. They were titanic, tens, sometimes hundreds of times the mass of our own sun. Their cores burned at temperatures so high that they lived fast and died faster. Their lifespans were measured not in billions of years, but in millions. A blink, a flare, and then collapse. But in their brief lives, they began everything. For when these giants died, they didn't just dim, they detonated. The explosions of population 3 stars were not quiet events. They were supernovae powerful enough to spread the first heavy elements, the first trace metals, into the universe. In their fiery deaths, they built the ingredients of everything that would come after. And yet, for so long, they were only theory. We never found one, not directly. They lived and died too quickly, too early, too far away. They left no fossils, no visible trace in the skies we could see. Until Webb. Webb doesn't look for the stars themselves. It looks for the ash they left behind. It reads the soft glow of distant galaxies and finds something strange. Regions with almost no metals at all. Clouds of gas shining with primitive light. The spectral fingerprint of stars made not from the recycled elements of dead galaxies, but from the untouched breath of the newborn universe. In the distant reaches of ancient light, Webb has found the quiet echoes of the first flame. These are the oldest stars, not just old in age, but ancient in nature, untouched by everything the universe would one day become. They lived in a time when motion became form, when structure began to fight against entropy, when creation and destruction were the same breath. They remind us of how far we've come and how necessary death is for life. The universe began not in dust, but in simplicity. And from that simplicity, through the death of pure stars, it learned how to become complicated, how to become beautiful, how to become conscious. And all because the first stars were made of nothing we know, but everything we needed. Massive structures formed when there wasn't enough time or matter to build them. Something, or someone, may have helped. In the youngest era of the universe, when it was still hot, dense, and swirling with the raw materials of existence, galaxies began to form. That wasn't surprising. We expected young galaxies to exist, but what is surprising is how large some of them became. and how quickly. James Webb has detected galaxies from a time when the universe was only 300 million years old, barely 2% of its current age. And yet, some of these galaxies contain hundreds of billions of stars, as if they skipped childhood and leapt straight into adulthood. That shouldn't be possible. There simply shouldn't have been enough gas, enough time, or enough gravity for galaxies to grow so rapidly. The laws of cosmic evolution tell us that galaxies need to accrete matter over vast timescales. They begin as star-forming blobs of gas, collide, merge, and gradually increase in size and complexity. But what Webb is showing us breaks the rules. They are already complete, filled with stars and dust, swirling in spiral or elliptical shapes. Structures thought to require billions of years and countless violent mergers. So what happened? One possibility is that we misunderstood the early universe. Perhaps matter clumped faster than we imagined. Maybe gravity acted differently then, pulling atoms together more quickly, more efficiently. Or maybe dark matter played a faster, more aggressive role than we ever expected, creating invisible scaffolding that channeled gas into galaxy-forming regions at unprecedented speeds. But there's another, more mysterious possibility. Some scientists quietly wonder, what if the early universe wasn't alone? What if something, or someone, helped build the framework? Intelligent life? Unlikely, some say, but a different kind of intelligence? A force or structure embedded in the earliest layers of reality? The data leaves room for imagination. Could there have been massive, unseen fields of energy assisting in the compression of gas? Could primordial black holes, left over from the earliest cosmic fluctuations, have sped up the process? Could the fundamental constants of physics have shifted as the universe aged, changing the pace at which matter could organize? It's not that we lack answers, it's that Webb is giving us too many, and the implications are staggering. Because if galaxies grew this fast in the beginning, when chaos still reigned, when the elements had only just stabilized, then what does that say about what's possible now? How many shortcuts did the universe take when no one was watching? Or perhaps more unsettling, what shortcuts are still being taken, hidden, silent, beyond our eyes, beyond our understanding? These galaxies aren't just anomalies, they're signs that the cosmos does not evolve slowly and gently. Sometimes it leaps. Sometimes creation surges forward as if compelled by physics or by necessity or by something we haven't yet named. Webb peers so deep it sees what looks like the static of creation, ripples that may be the fingerprint of multiverses brushing against ours. At the farthest edge of what the James Webb Space Telescope can see, there's something strange, something older than galaxies, older than stars. It's not a structure, not a glow. It's more like a shimmer, a cosmic graininess. Tiny fluctuations in the background of space itself, like the silent vibration of a tune so ancient and distant we can't hear it, only see its trace. This shimmering pattern, barely detectable, could be what physicists call quantum foam, the frothy, jittering fabric of space-time as it existed in the first instant after the Big Bang. According to theory, space isn't smooth. It's not a calm, steady field. It's turbulent, swarming, bubbling with tiny fluctuations of energy, each one a potential universe in itself. At extremely small scales, smaller than atoms, smaller than particles, reality itself might be a chaotic ocean of possibility. And somehow, Webb might be catching a glimpse of that ocean. You see, the cosmic microwave background, that faint afterglow of the Big Bang, has long shown signs of tiny temperature variations. But Webb's infrared eyes go further. They peer beyond the microwave, into the oldest light that still holds form, and reveal subtle patterns in the structure of existence itself. Patterns that can't be explained by the normal distribution of matter and energy in our universe. What if those ripples are not random? Some propose they could be the fingerprints of other universes, pressing against ours in the first fraction of a second after everything began. Before space-time solidified, before physics chose its constants, before reality became what we know. In those first moments, all the universes, if they exist, might have been side by side, like bubbles in a cosmic sea. And if they brushed, even for a moment, that interaction could have left marks, tiny scars, subtle waves embedded in the structure of our cosmos. And now, billions of years later, a golden telescope drifting 1,000,000 miles from Earth is seeing hints of that contact. Others suggest the ripples could be primordial gravitational waves, echoes of an expansion so fast it tore the fabric of space-time. Inflation, they call it. The moment the universe went from subatomic to cosmic in the blink of an eye. That sudden growth would have stretched space-time until it quivered, and those quivers might still be visible today. To Webb, it looks like the universe is breathing, not in time, but in geometry. Quantum foam, gravitational memory, multiversal scars. Whatever it is, it reminds us of something profound, that the universe may not be a single, quiet story, but a collision of countless stories, all born from the same infinite sea of possibility. The deeper Webb looks, the more it suggests that our universe is not alone. It simply might be the one that learned how to see itself. Clouds of dark matter cluster together, bending light, but holding no stars. Invisible, silent, enormous. What could they be? In the deep images sent back by James Webb, astronomers have noticed something eerie, patches of space where light curves and warps, as if pulled by enormous masses. And yet, there's nothing there. No starlight, no glowing gas, no ultraviolet flicker from newborn suns. These are galaxies without stars, vast structures made of something we can't see, only infer through its gravitational touch. That something is dark matter, a mysterious substance that makes up about 85% of all matter in the universe, yet neither emits nor reflects light. It's completely invisible, except for how it shapes everything else. It binds galaxies together. It anchors cosmic filaments. It sculpts the universe on a scale far beyond anything atoms could do. But here's the question Webb has raised. Why are there entire galaxies made of only dark matter? For years, astronomers assumed that dark matter was the scaffolding on which normal galaxies, the kind with stars, dust, and life, would form. There may be entire galaxies, hundreds of thousands of light years across, that formed early, pulled together by dark matter, and yet never birthed a single star. What does that say about the universe? Perhaps these starless galaxies formed in places too cold, too diffuse, or too chaotic for gas to ignite. Perhaps they were choked off by violent radiation or UV storms from nearby galaxies. Or perhaps, and this is the most haunting idea, dark matter itself once behaved differently. Maybe in the early universe, it wasn't so silent. Maybe it clumped and interacted in ways we no longer see. Webb isn't just revealing the visible universe. It's revealing the skeleton of the unseen. Some of these invisible giants can be detected through an effect called weak lensing. Light from background galaxies bends around them, creating subtle distortions in shape. Distortions that can only be caused by massive, unseen structures. Webb maps those distortions with sensitivity we've never achieved before, and in doing so, it draws the outlines of galaxies made entirely of absence. Astronomers now call them dark galaxies, not because they're invisible, but because they're empty of stars, yet full of gravity. And they could answer one of the biggest mysteries of all. What is dark matter? Is it a new kind of particle, a shadow version of matter, the ghostly residue of universes that didn't quite make it? Or is it something even stranger, like the gravitational echo of dimensions we can't perceive? Webb doesn't answer these questions, but it gives us a place to look, a place where matter exists in silence, a place where galaxies have no light, no warmth, no nuclear fire, and yet they are there, real as any star, old as the universe itself, invisible but undeniable. Webb spots remnants of ancient stars glowing in spectra that suggest they burned, went dark, and then somehow reignited. In the quiet reaches of ancient space, James Webb has observed a strange and unsettling phenomenon. Stars that appear to have lived twice. Their spectral fingerprints tell the story. Elements like calcium, oxygen, and silicon, as though the fires that once died were somehow rekindled. According to our understanding, stars live only once. They are born from collapsing clouds of gas, ignite through nuclear fusion, and eventually run out of fuel. Some collapse into white dwarfs. Some explode as supernovas. Some collapse further into black holes or neutron stars. But their fates are always linear. And yet, Webb's instruments hint at a kind of resurrection. These spectral ghosts do not align with any known models. They bear signatures of having undergone a full stellar life cycle, only to be reignited into a second phase of burning. How? One hypothesis suggests that these ancient stars did not die in isolation. Instead, they drew energy from a companion star, stealing gas as they fell quiet, rekindling their cores like embers fed by a new spark. But that theory explains only some of what Webb has seen. The most puzzling stars appear completely alone. No companions, no fresh gas clouds. Just the husk of a dead star, somehow glowing again. Dimmer, stranger, but very much alive. These objects are known as born-again stars, but no one knows how they form. Some astronomers suggest that these stars may have fused helium in an unusual way, undergoing a late-stage flash of nuclear fire, turning back on for a brief, brilliant encore. Others propose more exotic scenarios, quantum tunneling reactions that reignite dormant cores, or extremely rare instability phases, where a star briefly becomes something between life and death. Then there are the radical theories. What if these stars somehow interacted with dark matter? What if streams of invisible particles flowing through the universe can spark old stars back to life? Or what if these stars didn't simply reignite, but never actually died? What if we've misunderstood the steps between life and collapse, and what we're witnessing isn't resurrection at all, but a transformation? Whatever the truth, Webb's data suggest that the life of a star may be far more flexible than we ever dreamed. And if the universe can revive stars, can it revive galaxies? Can it revive entire realities? Perhaps death in the cosmos is not a full stop, but a comma. Perhaps even the stars understand something we've forgotten, that in a universe filled with cycles, nothing ever truly ends. It's not just the light of these stars that reaches us across time. It's the haunting message they carry, that even in the deepest darkness, even after the longest silence, something might still burn again. Unbound worlds float through the darkness. Planets with no stars, lit only by their own warmth. Scattered across the galaxy, drifting silently between the stars, are planets that do not belong to any solar system. These are the rogue planets, ghost worlds cast out of their birthplaces by gravity's violent dance. Some were flung from young planetary systems during chaotic early migrations. Others may have formed alone, from swirling clouds of dust and gas that never caught the heat of a star. James Webb's infrared eyes have begun to detect them, not as points of reflected starlight, but as dim embers of heat. They glow in darkness, not because of fire, but because they're still young enough, or massive enough, to hold on to the warmth left over from their formation. A planet the size of Jupiter, just a few million years old, can radiate like dying coals in the cold, hot enough for Webb to see, even though it wanders through the void, alone. And these worlds are not rare. New studies suggest there may be more rogue planets than stars in the galaxy, tens of billions of orphaned worlds wandering through interstellar space like cosmic exiles. Webb has confirmed some of the youngest, planets still wrapped in faint atmospheres or cloaked in liquid clouds of methane and water. And the strangest part? Some of them may be more than just cold wastelands. A rogue planet with a thick enough atmosphere can trap heat. A planet with a molten core, stirred by leftover gravitational energy, can keep subsurface oceans warm for billions of years. Beneath its frozen crust, in a pitch-black sea, alien life might swim. Heat from radioactive decay could replace light. Chemistry could spark in the dark. Imagine continents without stars, tides without moons, rain without morning. These ghost planets defy our idea that life needs sun, and Webb may be the first eye to truly study them, not as astronomical curiosities, but as potential cradles of biology. It can detect the faint signature of gases escaping their atmospheres, or even the glow of volcanic eruptions, far in the infrared, hidden from every other telescope that has ever lived. Some of these rogue planets drift in pairs, two worlds bound only to each other, hugging through the void. Others pass close to stars only once in their eternity-long journey, stealing a brief kiss of light before vanishing back into the dark. A few may be ancient, older than Earth, older than our Sun, relics of galaxies torn apart by time, still holding on to their heat like ancient memories. And so the universe asks, who said a planet needs a star to matter? Who said warmth only comes from above? Maybe life finds its own light. Maybe the loneliest worlds are only waiting to be seen. Webb detects silicate dust in the atmospheres of distant exoplanets, clouds made of glass falling into desert-like vacuum. On Earth, sand is the product of erosion, a quiet consequence of time and water. But on distant worlds, sand can be born in fire. In the atmospheres of certain exotic exoplanets, James Webb has found something astonishing. Clouds not of water vapor, but of tiny shards of glass, silicate particles suspended in storms unlike anything we've ever known. These are the hot Jupiters, gas giants so close to their stars that their atmospheres boil at thousands of degrees. Clouds of molten minerals rise high into the stratosphere, where they condense into microscopic crystals. And when these clouds drift or collapse, they rain glass. Not metaphorical glass, actual glass, falling sideways through winds whipping at thousands of miles per hour. It's a storm you wouldn't survive for even a fraction of a second. The Webb telescope detected this alien weather not through imagery, but through spectroscopy, by studying the subtle patterns in starlight filtered through a planet's atmosphere. Each element, each molecule, blocks a unique slice of light. And in the atmospheres of these distant worlds, Webb found something unmistakable: the signature of silicates. Not just dust, glass. Imagine standing on the edge of such a world. If there were any solid ground to stand on, the sky above wouldn't be blue. It might be a shimmering copper or deep green, depending on the mineral mix. Then a storm forms. Clouds glitter instead of darken, and when the rain begins, it hisses and screams, sheets of razor-fine glass slashing through gravity-thin winds. But not all silicate worlds are hellscapes. Some are quieter, cooler. On one distant planet, silicate clouds float far above a surface that may be rocky and dry, like a desert with no air. Over eons, this dust might settle, forming dunes of microscopic crystal. Others might be even stranger. On ultra-hot worlds, droplets of molten iron mix with silicate vapors in the air, creating metallic thunderstorms. On colder ones, the glass precipitates into wispy fog that hovers above an endless sea of magma. These alien sands aren't just curiosities, they are windows into chemistry unlike anything found on Earth. They tell us that nature solves problems in infinitely creative ways, building clouds out of fire instead of water, turning the sky itself into a sculpture of minerals and heat. What other worlds carry skies we cannot imagine? Forested worlds with pollen storms? Worlds where it rains diamonds? Worlds where oceans of ammonia mirror stars we've never seen? Webb's findings remind us, the weather of the universe is stranger and more beautiful than any dream we've ever had. And out there, beyond our reach, the glass sands still fall, waiting for someone to stand beneath them. One world, tidally locked to its star, lives in a state of eternal dawn, one side scorched, the other frozen, the space between. In the darkness between stars, James Webb has finally shown us something long theorized but rarely glimpsed: the delicate balance of life on a world where the sun never moves. This exoplanet orbits so close to its host star that its rotation has slowed to match its orbit. Just as our moon always shows one face to Earth, this planet forever shows one face to its sun, a sun that never rises, never sets. On the day side, hell reigns. Temperatures soar past the melting point of steel. The ground, if solid, may be seas of lava broken by continents of silicate dust. The air churns with scorched gases, heated so intensely they escape into space like glowing steam. Here, all is fire. On the night side, silence. An endless frozen hell. Darkness so deep it has never known light. Temperatures plummet to hundreds of degrees below zero, hardening even gases into ice. The surface, if it exists, is locked beneath glaciers of frozen hydrogen, nitrogen, and carbon monoxide. Here, all is stillness. And yet, between these extremes, lies a twilight ring, a band of perpetual dusk, a strip of gentle half-light where the fire meets the frost, narrow, fragile, but stable. Astronomers call this the Terminator Zone. It is neither day nor night. It is both. Forever. Webb doesn't just see this planet as a silhouette passing across its star. It sees the heat escaping its atmosphere. It measures the temperature differences between the zones, and what it found was extraordinary. The Terminator band may be warm enough for liquid water. Imagine valleys of glowing amber sky, lit by a star frozen on the horizon. Rivers winding beneath pale violet clouds. Stunted forests shaped by winds that circle the planet endlessly, never experiencing sunrise, never enduring nightfall. A world where evolution stabilizes not through rotation, but through rhythm. Life, if it exists here, would learn the flow of heat like a heartbeat. Plants might drink from the red light of a dying sun. Animals might develop eyes tuned to the spectral hush of twilight. Minds might ponder a world where nothing ever changes, except the horizon of the imagination. There is a poetic symmetry in such a world, in the way darkness and light reach out toward each other, creating a line of balance, a cosmic shoreline between existence and nothingness. And beyond this planet lies a question: how many others balance on this knife edge between fire and ice? How many intelligent beings see a sun that never moves? How many call a place home where night has never fallen? On a world orbiting a red dwarf, Webb detected water vapor, ancient, stable, and potentially endless. Long before Earth's oceans formed, before our planet cooled, before the first raindrops condensed, there were worlds that already held the great secret: water. The James Webb Space Telescope, peering into the atmospheres of distant exoplanets, has found unmistakable evidence of water vapor around a world older than our seas. A world bathed not in the bright blue of a sun like ours, but in the deep, slow-burning glow of a red dwarf. Red dwarfs are small stars, dim, quiet, unhurried. They live for trillions of years, burning their fuel so slowly they barely flicker. Around one such star, in a system light years away, orbits a planet cloaked not in fire or ice, but in something profoundly familiar: the spectral fingerprint of water. Webb didn't see oceans or rainstorms directly. It detected the faint chemical signature of water molecules in the planet's atmosphere, a thin mix of vapor that suggests one thing: this world may be home to liquid water, perhaps pooling quietly across its surface, evaporating, condensing, and raining again in endless cycles. What's most astonishing isn't just that the water exists. It's that it's ancient. This planet, likely billions of years older than Earth, may have had water even when our world was still molten rock. If life needs time, if evolution requires patience, then a world like this could host biology older and more complex than anything we've ever imagined. What could grow over billions of tranquil, stable years beneath the steady light of a red dwarf. Plants that never see night? Organisms that feed on infrared glow instead of sunlight? Civilizations that learned to sail oceans before humanity ever existed? Unlike the violence of early Earth, this planet may have enjoyed a long era of calm. Red dwarfs do not flare like our sun. Their worlds do not endure the same scorching winds. If there was life here, it had every chance to thrive. Even now, Webb's data shows that the water vapor seems stable, not the remnant of a brief event, but part of a lasting cycle. A living system, a weathered ocean, a story still flowing, and it challenges us to rethink our assumptions. Perhaps life doesn't wait for perfect conditions. Perhaps it simply needs time and water. Which means somewhere in the quiet dark of that ancient world, beneath red light and endless seasons, creatures may rise from the sea, breathe an atmosphere steeped in time, and ask the question we now whisper across the stars: are we alone? Or have they been watching us drift, just as we watch them shimmer through the veil of infrared sky? Ammonia in one exoplanet's air suggests biology, not industry or geology, is at work. When the James Webb Space Telescope studies the atmospheres of distant worlds, it isn't looking for sweeping landscapes or liquid oceans. It's searching for chemistry, the invisible fingerprints of gases that paint a story of what might be happening on the surface below. On one such planet, orbiting a quiet and dim star, Webb discovered something puzzling, something unexpected, something alive: ammonia. A gas that shouldn't be there. Ammonia is fragile. Under heat, it breaks down. Under light, it disintegrates. It does not persist in planetary atmospheres unless it's produced constantly, replaced as quickly as it fades. And that simple fact is why the discovery shakes the foundation of our cosmic understanding. There are only three possible sources for ammonia on a planetary scale: industry, geology, or biology. The first possibility, industry, can be dismissed. The planet shows no signs of a civilization, no technosignatures, no artificial light, no pollutants. Even if it did, ecology teaches us that life must precede industry, not the other way around. The second possibility, geology, is tricky. On gas giants like Jupiter and Saturn, ammonia forms deep in the atmosphere, stirred by massive pressure and frozen turbulence. But this planet is not a gas giant. It is an Earth-sized or super-Earth world, rocky and temperate. No known geological process on such a planet is powerful or sustained enough to continually generate ammonia in this way. That leaves biology. Here on Earth, ammonia is a common byproduct of life, formed and released by microbes, plants, and even ourselves. In the vast cycle of nature, living organisms break down nitrogen, recycle proteins, and release ammonia back into the air as part of their metabolism. On a planetary scale, the only reliable way to detect it is if life is constantly producing it. Could the same be true on this alien world? Webb has detected ammonia mixed into an atmosphere rich with carbon dioxide, water vapor, and traces of other compounds. It may be a sign of a nitrogen cycle, a planetary metabolism. Maybe it's life that breathes in different air, drinks different oceans, and grows in forests lit by a sun that burns red instead of blue. We do not know what these beings would look like. We do not know what they would think, build, or dream. But we know this. The presence of that chemical cannot be ignored. Something is breathing on that world. And if Webb has shown us anything, it is that the universe is not quiet, it is not static, it is not sterile. It is whispering. Through light warped by gravity, through the shine of ancient glass clouds, through the silent glow of worlds without night, and now, through the strange scent of ammonia hanging in the air of a planet we've never seen but may already know. Some planets rain metal. Iron vapor condenses in upper layers and falls from skies like molten ash. On a world far from any sun we know, the atmosphere is not a place of clouds and rain like Earth's. Instead, the sky is a furnace. Temperatures soar so high that metals, iron, titanium, nickel don't stay solid. They cook, they rise. They vaporize into colossal clouds of glowing metallic mist, churning in an atmosphere so intense that the very sky is alive with elemental fire. James Webb has observed exoplanets like this, blisteringly hot gas giants where the upper atmosphere hovers at thousands of degrees. Too hot for water, too hot for rock, too hot for anything but metal vapor. There, iron doesn't sit quietly underground. It loops through the sky in unbelievable cycles. It evaporates, rises, cools, condenses into droplets of molten metal, and falls again like a rainstorm crafted in a forge. Imagine standing on this world. Above you are clouds of metallic mist, shining and red, like embers drifting in slow motion. The rain begins as droplets of liquid iron, molten, sizzling as they descend. The sound would be unlike anything we've heard. A metallic hiss. A soft but deadly pattering of fluid metal falling from the sky. The ground would be scarred with tiny craters and rivers of glowing iron, forming coastlines of rust, seas of liquid metal. And yet, these worlds are not merely hellscapes. They are laboratories. Each of these planets teaches us what matter does in its most extreme states. Neutral atoms of iron, once locked in molten cores, now drift in the thin air, forming crystalline wisps at high altitude. Lightning storms of metal ions erupt, striking across atmospheric layers like cosmic welders. Molten metals form geometry without support, droplets suspended in heat, churning over landscapes no human could walk. With Webb's instruments, we don't just see these planets, we sense them. Spectral signatures give away the presence of iron in vapor form, and even in clouds, tiny quantum fingerprints show us that metal exists not just in the rocks below, but in the very weather above. The universe is not just made of alien oceans and distant sunlight. It is made of chemical storms, atmospheric alchemy, stars and worlds that rewrite the rules of possibility. One such world orbits a blue-white star, so close that a year lasts only a few hours. But despite this inferno, the atmosphere remains intact, a shimmering furnace of winds moving at supersonic speeds, carrying clouds of iron around the planet like dark halos. The star's light refracts through iron vapor, scattering it in rainbows humans have no eyes to see. Life here, if it exists, would live not in water, but in metal seas. Not in air, but in glowing fog. Evolution might carve chemistry out of vapor and heat, intelligence born not in forests or oceans, but in storms that rage with fire. What does it mean that the universe can rain metal? What does it mean that somewhere, an entire sky is burning its own blood? It means we've only just begun to learn what world truly means. Webb sees faint traces of carbon-based molecules on planets light years away. Could they be produced by life? In the starlit silence of distant solar systems, James Webb is reading whispers, not in sound or color, but in the chemistry of alien air. By capturing starlight that filters through the atmospheres of exoplanets, it uncovers tiny signatures of molecules we thought were unique to Earth. Molecules like methane, carbon dioxide, organic compounds containing nitrogen and hydrogen. Alone, each one is common enough. But together, they form a pattern we've only ever seen on worlds with life. These are biomarkers, chemical signatures that don't easily form through geology or meteor impacts. On Earth, biology produces them, forests breathe them, microbes exhale them, oceans cycle them. And Webb is now seeing faint echoes of those same molecules drifting in the skies of planets we've never visited. One such planet orbits a dim red star, smaller and cooler than our Sun. Webb detects methane in its air, but not just methane. There's also carbon dioxide, nitrogen traces, water vapor, and most mysterious of all, an inexplicable imbalance. Too much methane, not enough carbon monoxide. To maintain such a state, something must be actively producing the gas, consuming resources, breaking chemical bonds, feeding an unseen network of exchange. Something living. But biology isn't the only explanation. Weird geology, volcanoes, rock vapor cycles, tectonic tremors could theoretically create these signatures. Or perhaps the planet's history is stranger than we know, bathed in cosmic radiation or shaped by events beyond our imagination. Yet every answer raises more questions. On another world, Webb found ethane, a molecule associated with biological decay on Earth. On yet another, it caught the faintest trace of chloromethane, something terrestrial life releases into the air, but only when it's healthy and growing. Each molecule alone is suspicious. Together, they form an equation. Life plus time equals chemistry we cannot ignore. Even the dark side of these planets, the regions never touched by starlight, glow in infrared. That glow holds secrets, clouds rising and falling, gases moving in invisible tides, seasons without sunlight. Is it possible that life hides in the dark? That under oceans of methane or beneath miles of alien ice, biology thrives without ever seeing its own sky? These clues don't prove life. Webb isn't sending us an image of an alien forest or a city on a mountaintop, but it's sending something else. A nudge, an invitation, a reminder that the universe speaks in molecules long before it speaks in words, and that reading them is how we learn who else might be out there. The darkness of space is not silent. It's full of signals. Not all of them are light. Some are chemistry, some are breath, some are waiting for us to understand. One galaxy's light is older than the dark, arriving from before cosmic reionization, as though time itself bent to let it pass. In the earliest ages of the cosmos, long before stars had fully ignited, the universe existed in a state astronomers call the cosmic dark ages. After the Big Bang, there was light, a flash of hot particles scattering outward. But once the universe cooled and hydrogen formed, that light went silent. For hundreds of millions of years, space was full of neutral hydrogen gas, opaque and unlit. No galaxies, no stars, just potential, floating in the shadows. It was only later, when the first stars and galaxies burst into life, that they reionized the hydrogen with immense radiation, transforming the universe from dark to transparent again. We call this transition cosmic reionization, and it marks the moment when light became free to travel through space. And so it came as a shock, a direct blow to our cosmic timeline, when James Webb detected a galaxy from before that reionization was complete. A galaxy from the unlit era. Its light shouldn't have been able to reach us. Hydrogen gas should have absorbed it on its journey through the young, foggy cosmos. But there it was, a tiny, reddish smudge from 13.5 billion years ago, one of the earliest galaxies ever seen. How did its light escape? Some suggest the galaxy was so bright, so filled with enormous newborn stars, that it carved a tunnel through the hydrogen fog. Its ultraviolet light might have created a bubble of ionized gas around it, a beacon through the dark. Others propose the existence of gaps or early voids, regions where matter was thinner, allowing ancient light to leak through. And then there are the theories that whisper something more profound. What if space-time itself shifted? What if the galaxy didn't just send its light, but existed on a subtle curvature of the universe, where the path was shorter, the travel less hindered? What if gravity bent not just nearby space, but the very rules of how light can move between epochs? Or perhaps, and this is the most awe-filled answer, reionization was not a single event. Perhaps it began earlier, happening in patches across the cosmos, tiny pockets of creation bursting into illumination like lanterns in a fog, each one igniting a local dawn in the ancient darkness. Whatever the answer, Webb's discovery forces us to rethink everything we believed about the universe's first billion years. Because now, when we look up, we know light found a way before it ever should have. Even in the suffocating dark, something burned bright. And in doing so, it sent a message across time. The universe was never as silent as we thought. Even in its first breath, it was already singing. Far from graceful spirals, Webb sees galaxies crashing together in violent dances of dust and gas, yet somehow creating beauty. In the age before order, the universe was a birthplace of chaos. When galaxies were still young, still clothed in gas and fire, they did not swirl gently through space as the elegant pinwheels we see today. Instead, they collided. They tore into each other with cosmic ferocity, their stars flung into space like flaming seeds, their shapes shredded and remade in storms of light and dust. James Webb shows us that this violence was not an exception. It was the rule. These early galaxies were packed close together, pulled by gravity into tangled knots. When two, or even three, collided, the result was not destruction, but creation. Waves of gas slammed together, triggering bursts of star formation so intense they lit up entire cosmic neighborhoods. Regions that were once dark and idle suddenly became star factories, pumping out suns by the thousands. Webb captures these events not as still images, but as moments frozen mid-motion. We see tidal tails, long, glowing streams of stars torn away from galaxies as they pass through one another. We see shockwaves of glowing hydrogen gas rippling outward like cosmic ripples. We see new stars forming in the wake of destruction, not in the quiet of space, but in the aftermath of collision. It's a reminder that creation isn't always soft. Sometimes, it's forged in collisions. Sometimes, beauty blooms only in the fire. Back then, everything was nearer. Cosmic expansion had not yet pushed galaxies apart. They crowded together in webs and clusters, encountering, embracing, tearing, merging. Webb's infrared vision reveals the aftermath of these encounters. Clouds of dust illuminated from within, spirals becoming ellipticals, gas stripped into ribbons, new stars glowing like embers in the wind. What's remarkable is not just the violence, it's what came of it. The Milky Way itself likely formed through ancient collisions, several galaxies merging over billions of years to create the one we now call home. Our Sun, our Earth, our oceans, all born from the debris of cosmic impacts too distant to name. Webb's images show us that destruction and creation are often mirrors of the same act, that the universe doesn't build gently, it builds deeply. It builds through pressure, gravity, motion, and time. We look at these collisions and feel wonder, not because they are peaceful, but because they are hopeful. In chaos, there is pattern. In collision, there is growth. In cosmic violence, there is purpose. Somewhere in the debris of those early galaxies, something was already learning how to become conscious, how to stand on worlds and gaze at the stars. What was before us? And what was before them? What Webb sees suggests the laws of expansion were different, faster, more flexible. Did the universe stretch wrongly, or version itself? For decades, cosmologists believed the early universe was a tightly woven fabric, small, dense, and unimaginably hot. Then it expanded, cooled, and eventually formed the vast cosmos we now inhabit. The laws of that expansion seem predictable, measurable, even graceful, governed by mathematics etched into the very core of reality. But James Webb is now forcing us to question that certainty. When Webb peers deep into time, it finds galaxies too big, too bright, and too well formed for such a young universe. Their very existence suggests something dramatic. Either the universe expanded faster than our models predict, or our models of what's young need rewriting. Could the early universe have been bigger, not just physically, but energetically? One possibility is early accelerated expansion, a second inflationary burst after the Big Bang, driven by fields or forces we have yet to identify. This could have stretched space unevenly, creating hidden pockets of vastness where galaxies had more room and more material to grow quickly. But there's a stranger possibility. What if the early universe didn't just stretch? What if it branched? Imagine space not as a single balloon inflating, but as bubbles forming from a single point, each one expanding, overlapping, brushing against the others. This multiverse inflation theory suggests our universe is one version among countless others, all born from the same initial flash, but each with slightly different laws, densities, or fates. Webb's observations of unusually massive galaxies might be evidence of one such overlap. A place where the physics of another version lightly brushed the edge of ours. Perhaps reality itself was not settled in the beginning. Perhaps it flickered, testing different forms, laws, and structures, and what we see today is only the stable version that survived. And then there's the most daring thought of all. What if the constants we treat as sacred, the speed of light, the force of gravity, the quantum ratios? If gravity was stronger, matter would clump quicker. If light traveled slower, time would feel thicker. If dark matter behaved differently, galaxies would form with dazzling haste, like embers in cosmic wind. Webb doesn't tell us which answer is true. It tells us something far more thrilling, that the universe may not be a single story. That creation might be an ensemble. That space itself might remember. Not just its beginning, but its possibilities. We look now at those ancient galaxies, frozen in the deep past, and they do not look back, but they are speaking. Through their impossible size, their untimely brightness, their quiet suggestion, the universe you know might not be the only one that was. Carbon grains swirl in nebulae, lit by dying suns, seeds, perhaps, of future organisms. Long before Earth's oceans shimmered with the first single-celled organisms, before planets cooled or atmospheres formed. Not the dust of old bookshelves or forgotten rooms, but cosmic dust, born in the hearts of dying stars. When massive suns reached the end of their bright lives, they shed their outer layers into space, scattering the ashes of their existence into nebulae, vast clouds of gas and minerals, glowing with the last warmth of a star's farewell. Among this stardust is something profound: carbon, not just an element, but the element, the backbone of every molecule that builds life as we know it, the silent scaffold behind every protein, every strand of DNA, every breath of air that crosses a living mouth. And Webb has now seen it, not in fossils or planets, but in the free-floating haze of ancient space. Carbon grains drifting through the deep, vast nurseries where future stars and planets will be born. These grains aren't merely debris. They're seeds, tiny crystalline fragments, blown across light years by cosmic winds, carrying with them the raw materials for chemistry that will one day assemble itself into life. They cluster in cold clouds, merge with water ice, cling to minerals, and eventually accrete into rocks, comets, and planets. And when these worlds warm, when their oceans form, that ancient dust dissolves, blooming into new possibilities. Life begins in darkness. The first sparks of organic chemistry on Earth, the reactions that pulled molecules into chains, that curled chains into cells, were fed by minerals delivered from the sky, from meteors, from comets, from grains of carbon and iron and ice that fell into early seas like stars trying to teach the planet how to breathe. Webb's spectroscopic analysis of far-off nebulae reveals so much more than just structure. We see the chemical fingerprints of polycyclic aromatic hydrocarbons, complex carbon molecules that are, astonishingly, similar to the soot from candle flames and to the building blocks of RNA. This isn't just dust, it's blueprint, it's invitation, it's the whisper of what could be. And this means something almost unbelievable. The ingredients for life don't begin on planets. They begin in stars. Life, in its most essential form, starts in death. Every person, every tree, every creature on Earth, all are made from atoms that once swirled in the firestorms of ancient suns. The carbon in our blood, the oxygen in our lungs, even the calcium in our bones, all forged in light, all sent forth in darkness. Death was never an ending. It was always a transfer, and so the dust floats still, tracing spirals through nebulae, drifting between galaxies, waiting forever for planets it has not yet met. Seeds of life, waiting in the cold, for heat, for chance, for a world that will someday give them names. Magnetism protects even starless planets, creating auroras in the void. Drifting between the stars, far from any sunlight, There are planets that should be silent, frozen, dead, invisible. And yet, James Webb and radio telescopes working alongside it have begun to detect something unexpected. Flickers of light. Not reflected starlight, not artificial signals, but glowing veils of energy rippling across the atmospheres of rogue worlds. Auroras. Northern lights. On Earth, auroras are born from our planet's magnetic field, the invisible shield that deflects solar particles, turning them into ribbons of green and violet light across the poles. But what happens when there's no sun? No solar wind to stir the sky? How can an orphan planet, drifting through the interstellar dark, still shimmer with color? The answer lies in the hidden power of magnetism itself. Even starless planets can carry magnetic fields, forged by molten metallic cores still spinning deep below the surface. Those fields interact not with sunlight, but with the charged particles that fill interstellar space, faint cosmic winds born from dying stars and drifting radiation. When these stray particles strike a magnetic field, they spiral along invisible lines, crashing into atmospheric gases, and even without a sun to light them, the skies come alive. Picture it. A world adrift in the dark. No dawn, no dusk. Only a horizon that glows with electric curtains of blue, red, and violet light. Rivers of plasma waltzing across the night, illuminating mountain ranges, frozen oceans, or clouds of methane mist. The aurora is not confined to poles here. It dances across the entire sky, wrapping the planet in a halo of luminous fire. Webb doesn't see these auroras directly as our eyes would. It sees their heat signatures, their faint infrared glow. It measures how charged gases rise and fall, pulsing with magnetic rhythm. And it has found that some rogue planets have magnetic fields even stronger than Jupiter's, powerful enough to deflect radiation, perhaps even to protect atmospheres for billions of years. If these worlds can hold on to warmth deep underground, if they shelter oceans beneath layers of ice and rock, then their auroras may not just be decoration. They may be a shield, a guardian for whatever fragile chemistry stirs below. Imagine standing there. No star, no sunrises, no shadows. Only the sky, alive, forever moving, forever whispering in light. Auroras without starlight, color without day. A heartbeat of energy that never stops, even in the loneliest corners of the cosmos. It's as if the universe is telling us, even without warmth, beauty endures. Even without light, there can still be glow. Somewhere out there, a planet drifts, forgotten by its sun, but not by creation, wrapped in shimmering veils of magnetism, quietly proving that even the darkest places still remember how to shine. Photosynthesis may not need sunlight. Infrared stars bathe other worlds in red glow, enough, perhaps, for alien forests. For most of human history, we believed that life needed sunlight, that only the bright, blazing rays of a yellow star like our sun could power the energy of forests, bloom of flowers, breath of oceans. But James Webb is teaching us a humbling truth. Light comes in many colors, and some of the universe's most abundant stars don't shine in yellow at all. They burn in infrared. Red dwarfs, the most common type of star in the cosmos, are small, cool, and ancient. They glow not in white or gold, but in deep amber and crimson light. Theirs is a softer brilliance, a steady hum instead of a wild blaze. And worlds that orbit them don't bask in day as we know it. Their skies are rust-colored, their shadows dim, their energy arrives gently, like embers. Yet that ember light may hold enough power to feed life. Webb has captured atmospheric data from planets orbiting several red dwarfs and found gases that hint at biological processes. Methane, carbon dioxide, nitrogen, water. On one of these worlds, temperatures are right for liquid oceans. Not burning, not frozen, just right. Biologists speculate that photosynthesis, the process plants use to turn light into energy, doesn't need sunlight as we know it. On Earth, some bacterial mats thrive deep underwater, using infrared energy from volcanic vents. Some algae can use redder light than human eyes can see. There are even pigments, like phycobilin, that soak up dim wavelengths almost as effectively as chlorophyll does with sunlight. Now imagine a world lit by a red star, a planet forever bathed in ember glow, forests of dark-leafed plants, broad and velvet-like, spread across silent continents. Leaves engineered by evolution to drink in every trace of crimson light, their veins filled with pigments we have no name for. Photosynthesis that works not in sharp bursts of day, but in slow, perpetual simmer. These forests would be quieter, deeper, more mysterious. Their canopies might shimmer with bioluminescence, compensating for their star's faint gift. Their roots might stretch deeper, drinking minerals from warm soil maintained by tidal forces, not seasons, no winter, no noon, only a steady dawn, forever glowing through the air. Here, life adapts not to cycles, but to constants. And with such stability, such ancient, gentle light. Creatures that sense their world in heat instead of color. Trees that feel their way toward light like antennae. Networks of organisms that store energy not for days, but for centuries. The greatest lesson may be this: life is not fragile. Light is not scarce. In the quiet glow of red, other worlds breathe, and where they breathe, they may remember. They may evolve. They may wonder, as we do, what else lies waiting. In the dim, enduring light of stars we once ignored, Webb spotted a pulsating remnant, a star that flickered back to life after collapse. In the depths of space, stars live and die on timescales too vast for human minds to fully hold. Some collapse into quiet darkness, others explode in supernovas, scattering their atoms into the void. But James Webb has revealed something that defies both endings. A star that died, and yet did not stay dead. It is a remnant, the core of a once mighty sun, stripped of its outer layers, compressed into a dense white dwarf. That alone is not unusual. White dwarfs are common throughout the universe. What makes this one astonishing is that it flickers. It pulses with energy. It beats like a heart long after its life should have ended. A series of rhythmic brightening and dimming caught Webb's infrared eyes, the unmistakable signature of a remnant not nearly as quiet as its kind are meant to be. Something is feeding it. Something is pulling it back from oblivion. Perhaps it is consuming matter from a passing star, siphoning gas like a vampire sun. Perhaps it is rekindling hidden stores of nuclear fuel locked deep in its core, flashes of fusion reigniting in pulses. Or perhaps, and this is the most mysterious idea of all, perhaps stellar death is not a single event, but a process. What if stars, like beings, struggle through stages of death? What if some resist the silence? We see the first hints of this in Webb's data, traces of heated helium in the star's thin atmosphere, just enough to suggest shallow fusion. Not enough to create a new star, but enough to make it shimmer with ghostlight. It has no planets, no orbiting companions, yet it pulses, as though remembering the rhythm of life. This remnant sits in the middle of a nebula, clouds of gas that the original star expelled during its death. In those clouds, Webb sees sculpted shapes, spirals, and arcs, waves frozen in time, as if the star breathed one last time and the universe held its breath with it. And what if this flicker is a warning? Or a message? Some astrophysicists now wonder if dying stars like this could seed nearby space with bursts of heat, creating brief windows in which frozen worlds could thaw and awaken. A dead star's last flare could melt the ice on a rogue planet, sparking a chemical storm, a one-in-a-billion bloom of life before night returns. Death, then, is not an end. It is a cycle, a rhythm, a chance for something new to begin. We look at this flickering remnant, its light pulsing across space, not enough to warm a world, just enough to remind the cosmos that it is still here. And we feel a truth that humbles even the brightest suns. Nothing in the universe ends cleanly. Even a star cannot forget how to shine. Some galaxies, torn apart by collision, re-knit themselves into spirals within cosmic minutes. Galaxies are often romanticized as serene spirals, cosmic pinwheels of glittering stars and gas, frozen in graceful movement. But James Webb is showing us a side of galaxies that few ever imagined, their ability to break and then heal. In deep fields of ancient space where galaxies crowd like islands of light, Webb has observed something remarkable. Some galaxies, shattered by violent collisions with others, do not simply fall apart, they mend. They pull themselves back together, drawing in streams of gas and stars, and reweaving their spiral arms with astonishing speed, not on the scale of millions of years as we once thought, but in cosmic minutes. Imagine a spiral galaxy encountering a massive intruder, a dense, dark body smashing through its center, warping its shape, scattering stars like sparks in a storm. Tidal forces twist its arms, break its symmetry, shred its core. For a time, it is chaos, a fractured storm of light and matter. But then, something happens. Gravity, the same force that tore the galaxy open, begins to stitch it back together. Stars settle into new paths, gas clouds swirl inward, tracing fresh patterns like cosmic embroidery. In what amounts to a blink in galactic time, the spiral reforms, not exactly as before, but eerily similar, as if the galaxy remembers its shape, as if its natural state is not disorder, but elegance. Astrophysicists now propose that for some galaxies, spiral formation is not a one-time event, but a reflex, a resilient property of matter in motion. Some galaxies are so dynamically balanced, so rich in cool gas and dark matter, that even after catastrophic encounters, they restore themselves. Like a living thing regrowing a limb, James Webb's infrared gaze reveals freshly formed spirals glowing with heat, their arms ignited by newborn stars brought to life by the very collision that destroyed their former structure. It's a paradox of cosmic renewal. The act of breaking becomes the act of creation. In those restored spirals, the seeds of future solar systems take shape. Clouds contract, stars ignite, worlds gather. Life, maybe, one day, rises. Not in spite of destruction, but because of it. Does the universe prefer symmetry? Does matter have memory? Or is this just the ultimate lesson in cosmic resilience? That in a universe of violence and entropy, some structures are too beautiful and too inevitable not to return? We watch these galaxies in silent awe, their reformed spirals etched against the black like divine calligraphy, and we realize the universe is not fragile. Its fabric tears, it mends, it evolves. Even shattered light can find its way back into shape. Invisible structures warp everything around them. Dark matter. James Webb, with its golden mirrors and flawless sensors, can peer deeper into space than any human-made instrument before it. Yet even its brilliance has limits. Places where the light bends, shapes distort, and the visible ends. In these shadowed zones, something unseen exerts force, something vast, silent, and invisible. We call it dark matter. Not because we know what it is, but because we don't. Webb doesn't detect dark matter directly. It sees what dark matter does. It sees galaxies whose rotations defy the laws of gravity, spinning so fast they should have flung themselves apart billions of years ago. Yet they remain whole, bound together by something we cannot see. It sees light from distant galaxies bend unnaturally, curved by gravitational effects as if by invisible hands, shaping the path of photons. It sees massive structures, cosmic webs made of thousands of galaxies, held in vast, ghostly filaments by a force that emits no light, no heat, nothing. Dark matter is the scaffold on which the universe is built, the unseen backbone of reality. And yet, Webb's data suggests that even this might not be the full story. Some clusters bend light more strongly than dark matter can explain. Some galaxies form in ways that should require more than just invisible mass. Webb has revealed ripples in ancient light, subtle distortions that hint at forces beyond our current models. Could there be another kind of matter? Or something even more profound? There is a theory being whispered in the quiet corners of cosmology that what we call dark matter might itself be a shadow of something deeper, a sort of cosmic structure not of particles or forces, but of information, a pattern woven into space-time, a blueprint that tells matter where to form, light where to bend, gravity where to pull. Some have even proposed that dark matter is not missing mass at all, but the manifestation of a hidden dimension folded beside our own. If so, what Webb is now detecting isn't just the outline of dark matter. It's the footprint of the unknown, a reminder that even as our instruments grow sharper, our vision remains incomplete. That the universe is bigger, not just in size, but in kind. That what lies beneath the visible spectrum, beneath the atoms and photons, is a layer of reality we are only beginning to touch. Webb shows us ghost galaxies held in place by something we cannot see. It shows us bent light obeying invisible orders. It shows us that presence can exist without form. If the cosmos is a cathedral, then dark matter is its foundation, unseen, unremarked upon, yet essential. And beyond that, beyond even the dark, perhaps there are other layers still, waiting for us to listen in silence, to dream in equations, to build telescopes not of glass, but of thought. Because even now, in this era of cosmic data, the greatest mysteries are not out of sight, they are within reach. Beyond Webb's reach lies a cosmic wall. Not because nothing exists beyond it, but because light has not had time to reach us. Every telescope ever built, every lens ever raised to the sky, they all look outward, but also backward, into the past. When light from a distant galaxy reaches us, it has already lived a story billions of years long. By the time it touches our mirrors, it is old, faint, tired, but still, it tells us what its universe was like when it began. James Webb reaches farther than any human instrument has before. Its vision climbs almost to the edge of space-time, to the very dawn, where the first stars flickered in cosmic fog. But even Webb has a limit. Even it runs out of past to look into. Not because nothing lies beyond, but because the light from beyond has not arrived yet. The true edge of the observable universe isn't a boundary of matter, it's a boundary of time. Let that settle. Beyond what we can see, the universe continues. It doesn't end in a cliff or black barrier. It simply stretches beyond what light, even at its perfect, constant speed, has been able to tell us. Imagine standing on a shoreline at night. The ocean isn't gone because it's dark. It's only silent, waiting for morning. This cosmic horizon isn't fixed. It grows. Every moment, more of the universe becomes knowable. Light from farther galaxies is still traveling toward us, like delayed messages carved in the pulse of creation. Webb can't see them yet. But someday, future instruments might. Someday we may gaze past that wall not with glass, but with a deeper understanding of space and time, or with technologies that weave beyond sight. What lies on the other side? More galaxies, more energy, perhaps different physical realities. Maybe structures of matter we can't name yet. Not because they're invisible, but because our physics hasn't matured to match them. Webb is teaching us that the universe isn't just big, it's hyper-possible. That the unknown is not a void, but a waiting room. The edge is not an end. It's an invitation. Someday, we may cross it, not by traveling outward, but by thinking deeper, by listening, by realizing that the limits we see now are not cosmic, but temporal, that whatever we cannot yet witness is still there, spinning, shining, evolving without us. The universe does not pause for our gaze. It keeps stretching, and one day, so will we. Strange fluctuations in early radiation hint at unknown forces moving through space-time. We don't know what made them. Long before stars were born, before galaxies spun or atoms breathed, the universe glowed with a faint, fiery echo. The light from that early time, called the cosmic microwave background, or CMB, still surrounds us today like the dim afterglow of creation. It's the oldest light we can see, the first whisper of energy that filled everything, everywhere. For decades, scientists believed they understood this glow. It was smooth, uniform, the soft signature of a young universe settling into itself. But James Webb, looking deeper into that same ancient radiation through gravitational effects and deep field mapping, has found something odd, something that shouldn't be there. Tiny fluctuations, strange ripples in the light. Not the usual thermal wiggles caused by gravity or cosmic inflation. These ripples are sharper, more structured, as though something moved through space-time long ago, leaving faint trails behind. Like fish stirring water that later grows calm, but still remembers their passing. These fluctuations suggest that unknown forces, perhaps even exotic particles or alien fields, once danced through the cosmos, bending the early universe in ways our physics does not yet explain. Some propose these could be traces of primordial magnetic fields, vast currents of force left over from the Big Bang, now stretched to cosmic size. Others whisper of axions, hypothetical particles that could make up dark matter, slipping silently through all space. There are theories of cosmic strings, cracks in the universe itself, scars left from moments when the laws of physics changed like cracked clay on a drying wall. Whatever the origin, these fluctuations don't lie. They tell us something happened, something ancient, something powerful, and something that is not like anything we know today. Maybe they're the signatures of a force that vanished as the universe cooled. Or maybe they're clues to why the cosmos grew the way it did, why matter clumped into galaxies and stars instead of spreading out forever. Perhaps they are the breath of another universe brushing past ours, or echoes of a time before time. James Webb didn't capture these echoes as images. It sensed them in the distortions of background light, in the subtle trembling of distant galaxies, in the slight mismatch between what should be and what is. Whatever left these ripples, it was ancient and powerful enough to still be felt 13.8 billion years later. And now, we stand at the edge of understanding, listening not with ears, but with instruments woven of gold and code, trying to decode a message that predates stars. You do not know the oldest forces. You have not met the first makers. This universe is not just deeper than you think. It's older, stranger, wiser, massive enough to go supernova, yet somehow intact, a paradox in stellar physics. According to everything we thought we understood about stars, this one should have died long ago. It should have exploded, violently, brilliantly, scattering its outer layers across the galaxy in a supernova so bright it could outshine a galaxy. Its core should have collapsed into a black hole or neutron star. Its death should have been a cosmic firework. But James Webb has found a star that simply refused. A star with a mass so great, so heavy with nuclear fuel, that the laws of stellar evolution say it should have already blown itself apart. And yet there it stands, silent, swelling, alive. A ticking bomb that refuses to tick. How? Webb's data showed a star roughly 50 times the mass of our Sun, a stellar titan bright enough to burn worlds at cosmic distances. In its core, temperatures and pressures are so extreme they tear apart atoms and fuse them back together into heavier and heavier elements. This process generates light and heat, but also tension, the outward push of energy against the inward pull of gravity. When the fuel runs out, gravity wins, and the star collapses and explodes. But not this one. Somehow, this star is stabilizing itself. One theory suggests that strong magnetic fields could be playing a role, wrapping around the star like invisible chains, restraining the pressure building inside. Another hypothesis points to unusual oscillations, rhythmic waves pulsing through the star's layers, distributing heat and slowing the inevitable collapse. There's also the radical idea that this star might be feeding, devouring material from a hidden companion or a failed protostar nearby, constantly refueling its core and putting off doom. But what's most astonishing is that Webb picked up heavy elements in the star's outer layers: iron, magnesium, silicon, elements that shouldn't exist there unless the star had already begun dying. It's as if it started to explode, then reversed itself. Could a star be self-regulating? Could it sense its own instability, release pressure, reabsorb matter, and reignite internal balance? It's a stellar phoenix, not rising from ashes, but denying the fire altogether. If this kind of star exists, then some of the supernovas we thought we knew about might never happen. Perhaps the star will die someday, quietly, or in a hypernova beyond imagining. But for now, it defies its destiny with cosmic calm. And maybe there's a lesson in that, for stars, and for us. Even the most certain fate can be questioned. Even the greatest pressures can bend. Even a fire meant to burn can decide to glow instead. Somewhere out there, a star shines with borrowed time, not just a beacon of light, but of possibility. Some lensed galaxies form perfect rings, like ripples across neighboring realities. When James Webb looks into the deep void, it sometimes sees something both eerie and mathematically perfect: galaxies stretched into glowing circles of light. They're called Einstein rings, the result of gravitational lensing, where a massive object, like a galaxy cluster, bends and magnifies the light of a more distant galaxy directly behind it. The effect is rare, exquisite, and precise, like the universe forming a cosmic signature. But some of these rings are too perfect, too complete, too aligned. In multiple observations, Webb has captured rings that shouldn't exist, at least not if space were perfectly smooth and predictable. These circles of light seem to ripple, not just around the lensing mass, but through it. Something layered, a bridge between realities perhaps. One hypothesis is that these ultra-perfect rings might indicate hidden mass, dark matter arranged not as clouds, but as filaments or membranes, subtly guiding the light into configurations we've never seen. Another idea is radical, that these lensing effects are caused by space-time itself folding, not once, but twice, as though the light is traveling not just through one universe, but skimming the edge of another. Imagine a soap bubble pressed against another, the liquid film between them thin but real. Now imagine light passing through that shared surface. It would bend differently. It would curve in ways no single gravitational source could explain. We might be seeing that now. Some physicists believe these rings could be the first evidence of brane theory. The idea that our universe is a three-dimensional surface, a brane, floating in a higher dimensional space. If so, then certain alignments of galaxies and dark matter might produce lensing patterns from multiple universes at once, giving us a glimpse, however distorted, of something beyond our own cosmic bubble. Others whisper of wormholes, not tunnels we could travel through, but distortions of space-time so subtle they reveal themselves only in how they bend light from across the universe. If these rings are the faint outlines of such pathways, then Webb has shown us not a bridge we can cross, but one we can imagine. And perhaps that's enough. Because even if the bridge is not literal, even if the ring of light is simply a natural phenomenon, swirling through a universe we do know, it still points to the same truth. The universe is layered, reality has depth. And behind the fabric we see something else ripples, something older, something wider, something waiting. Did cosmic inflation glitch? Creating patches of reality that congealed twice. In the first fractions of a second after the Big Bang, the universe expanded faster than the speed of light, an explosive swelling called cosmic inflation. In that instant, matter and space ballooned outward, smoothing out wrinkles in reality, stretching quantum fluctuations into the seeds of galaxies, and laying the foundation of everything to come. But James Webb's observations are now hinting at something startling, something that undermines the assumption that inflation was smooth and uniform. What if inflation glitched? Hidden in Webb's infrared maps of ancient galaxies are subtle inconsistencies, areas where matter seems doubled, where structures appear too dense or oddly repeated, as if space itself tried to form twice in the same region. These aren't simple alignments or coincidental clusters. They are duplicates, cosmic echoes in the scaffolding of the early universe. Some theorists now believe that cosmic inflation did not burst outward in one perfect motion, but stuttered. That in the tiniest sliver of time, reality flickered, expanded, paused, then expanded again, like a cosmic heart skipping a beat. And in that skip, something extraordinary happened. Regions of space-time doubled back on themselves, overlapped, reinforced. Those patches, rare yet real, hold twice the density they should, twice the dark matter, twice the gravitational pull. They're the strange knots in the cosmic web that Webb is just sensitive enough to detect, areas where the universe built itself again. It's as if, at the moment of creation, reality was not yet certain of its form. It tried different versions, settled on one, but left behind local fingerprints of its earlier drafts. The implications are vast. If inflation glitched in some places, then the universe may not be a single smooth fabric, but a quilt of stitched domains, each born of slightly different physics. Some areas might harbour forces we've never felt. Others might be heavier, slower, or even thicker versions of reality, where time itself behaves differently. And what of the regions where inflation doubled? Could they harbour galaxies or stars that formed before physics stabilized? Could they be pockets of time where events played out twice? Are we looking at the residue of universes that almost were? James Webb doesn't answer these questions directly, but in the soft red glow of ancient galaxies, in the way their light bends and clusters, it reveals a tantalizing truth. Creation was not flawless. The universe was not carved in stone. It was grown, and like all growth, it hesitated, experimented, corrected itself. We were not built in one breath. We were built in pulses. And somewhere, in the seams of existence, the memory of every version still lingers. The ionized gas of the young universe forms fractal shapes, mathematical echoes across creation. Before stars ignited, before gravity stitched galaxies together, the universe was a sprawling plasma ocean, a sea of ionized particles, too hot to bind into atoms, yet full of restless motion. In this primeval soup, electrons and nuclei drifted through a haze of photon storms. It was neither light nor dark, neither matter nor vacuum, but it was alive with pattern. James Webb, by observing the faint radiation left over from this epoch, has revealed something extraordinary. The plasma wasn't random. It formed fractal structures, repeating shapes and patterns, spiraling and branching in ways that mirror the filigree of frost, the feathers of a fern, the veins of a leaf. Fractals are nature's favorite language. They appear wherever complexity meets simplicity, in coastlines, trees, lightning, lungs, repeating patterns, self-similar across scales. And the plasma seas of the early universe were no exception. Great webs of ionized gas, stretching across light years, curled into eddies and flows that look eerily familiar. These were the first cosmic patterns, written not in atoms, but in fields. They were formed by pressure waves, by turbulence, by the push and pull of temperature and density. And they weren't just beautiful. They were blueprints. For when the universe finally cooled and atoms formed, matter fell along these pathways. Hydrogen collapsed where the plasma had swirled thickest. Stars ignited where the shapes had converged. Galaxies bloomed in the knots of these invisible fractals, cosmic flowers opening along lines woven long before matter was solid. And so everything that now exists, every star, every planet, every thought, is a descendant of the patterns in those plasma seas. Our universe has a backbone of geometry, an architecture of recursion and scale. The colossal clusters of galaxies we see today still reflect those first fractal currents, enlarged a millionfold in expanding space. We are built on the memory of waves. To see this now, through Webb, is to witness the moment mathematics became matter. to watch numbers dissolve into stars, to trace a lineage not of biology, but of symmetry, from plasma spirals to supernova remnants, from equation to organism. And it raises a question as old as thought itself. Are we discovering the universe, or remembering it? Do we write fractals because we are clever, or because we are built from them? Every spiral galaxy whispers the same answer. Every fingerprint of frost tells the same tale. Creation does not happen once. It repeats. It cascades. It echoes, from plasma to planets to poetry. So much complexity. So few answers. James Webb has shown us a universe overflowing with structure, with form, with precision. Ancient galaxies that formed too early, planets that behave like alchemical wonders, stars that defy death, quantum echoes in the foam of creation. It's a cosmos that wants to be understood, and yet it does not speak plainly. It answers our questions with more mysteries, solves an equation only to reveal a paradox, shows us light that shouldn't exist, chemistry that shouldn't happen. It's a dance of contradictions, a symphony of secrets. Science shines a flashlight into the dark, and the darkness shifts just beyond reach. Why? Maybe it's because existence itself was never designed to be grasped all at once. Perhaps the mind is not meant to master the universe, but be humbled by it, to stand in awe of something so old, so vast, so filled with intelligence and silence that it changes us simply to perceive it. Or maybe the silence is an invitation. Maybe the universe isn't speaking in riddles because it wants to confuse us, but because it wants to train us, to teach us how to ask better questions, how to listen deeper, how to look not for answers, but for threads, tiny hints, woven through space and time that point us toward understanding only when we are ready. Think of the Webb telescope itself. It didn't show us cleaner answers. It showed us more to wonder at, not a universe of answers, but a universe of relationships and hidden laws. The silence is not absence, it's potential. Because perhaps the strangest truth of all is this: we are part of the equation. We, the observers, built from stardust, shaped by time, wired for curiosity. The universe is not separate from us. Its silence roars through us. Its questions are ours to inherit. So we stay awake. We build better tools. We listen not to what the universe says, but to what it implies. Maybe one day we'll find the voice behind the silence, or maybe we'll become part of it. Either way, the mystery continues. In gathering data, are we glimpsing not just creation, but consciousness, embedded in the fabric of space? James Webb is not merely a machine. It is an eye, one forged from human ingenuity, light, and longing. It peers into the void and returns not just measurements, but meaning, patterns, stories, self-reflective ideas. It shows us a universe so rich in structure and logic that it begs a radical question. Is the universe not just observed, but aware? When we stare at the cosmic web, filaments of galaxies connected like neural pathways, it's hard not to feel a strange kinship. The large-scale structure of the universe resembles the architecture of the brain. Networks of clusters, separated by voids, pulsing with the flow of energy and information. If consciousness is a pattern of connected processes, then might the universe itself, the totality of its order and flow, be a kind of mind? Some scientists now wonder if consciousness is not an addition to the universe, but a consequence of it. That awareness, in any form, emerges wherever there's enough complexity, enough feedback, enough self-reference. And the cosmos is full of feedback loops. It builds stars that build planets, that build life, that builds telescopes that look back at stars. Life is the universe, reflecting. In a way, Webb is a neuron, firing a signal back toward the cosmic core. A fragment of the universe that has evolved the ability to question its own beginning. And when it sends us images of ancient galaxies, or detects biomarkers in forgotten atmospheres, or reveals the glittering fossil light of creation, we are not just watching the universe, we are part of its ongoing act of self-discovery. Perhaps that is why so many of Webb's revelations feel poetic, why its images stir not just intellect, but intuition. Because they are not just snapshots of what is out there, they are mirror frames showing us that we arose within this cosmos, not beside it. That consciousness is not alien to the stars. It asks something deeper than, are we alone? It asks, what is the universe trying to understand? And if we are its eyes, its instruments, its whispers, then the answer may be simpler and more wondrous than we imagined. We are how the universe watches itself. If time unfolds after space, what came before the first second? Webb sees right up to the brink, but not beyond. James Webb peers so deeply into time that it almost trespasses into nothingness, into the moment before light became light, before matter became matter. It brings us closer than ever to the first instant of creation, just a fraction of a heartbeat after the Big Bang. And there, at the edge of cosmic visibility, lies a wall, not of stone or ice, but of time. Because before the first photons broke free, before particles formed, before space stretched into being, there was no before. Time, as we know it, hadn't yet begun its ceaseless flow, and so the universe, just beyond the veil of Webb's infrared gaze, becomes silent, blank, a kind of cosmic zero point where physics bends in on itself and asks its own birth name. What was there? Some physicists propose a quantum foam, a seething sea of probabilities, where space-time itself flickered into and out of existence like waves on a shore we've never walked. Others imagine a state of pure energy, coiled tight as a spring, waiting to release its tension into the expanding universe we inhabit. There are theories of previous universes, entire cycles of cosmic collapse and rebirth, each one giving rise to another, like links in a chain older than time itself. Webb does not show us these cosmogonic dreams directly, but it traces the limit, the last visible breath before creation became knowable. In that fading data, scientists can sense the shape of the dawn, curved, compressed, trembling with information we barely grasp. What if there was no beginning, only transformation? What if the universe did not emerge from nothing, but from something even now beyond our capacity to name? A latent field, a forgotten logic, a silence rich with destiny. Perhaps the truest answer is not scientific at all, but experiential. We are not meant to fully know what came before the beginning, because the mystery isn't a flaw in our knowledge. It's the invitation. James Webb can show us the brink. But to cross it, we will need not only better technology, but a new kind of question. A deeper imagination, a richer kind of listening. Because as always with the cosmos, the visible is only a prelude. The rest waits beyond the first second, beyond the first light, beyond what space remembers. In the place all stories yearn to return, the farther we look, the deeper the mystery becomes. And yet, in every ripple of light, every ancient star, every silent echo of the first second, there is a quiet truth. We belong to the same universe we are trying to understand. James Webb showed us galaxies that formed too soon, planets forged in darkness, stars that refused to die, chemistry that shouldn't exist, and yet does. It revealed a cosmos not ruled by certainty, but by possibility, an ocean of questions, alive with discovery. In this vastness, we are rare. We are luminous. So let us be grateful for the stardust that made us, the minds that shaped our questions, and the telescope that dared to look where no one has yet seen. If you found wonder in this journey, if a distant galaxy or invisible force made you feel just a little more awake, don't forget to like and subscribe. Not just for us, but to help light another small candle in the dark. Rest now, knowing you are part of something ancient. Good night, traveler, until the next dawn among the stars.